Okay, so good evening, everyone, and I welcome you all to today's live session. Today is week 11's live session of the course Nonlinear Vibration, NOC24 ME54, and this is our second last live session. However, I have also scheduled a extra session about which details you'll get through mail. Okay, so this course is being taught by Professor S.K. Dwivedi of IIT Guwahati, and I'm Rashi Aditi Ranjan. I am a NPTEL PMRF TA, and also I'm a PMRF scholar in the Department of Mechanical Engineering, IIT Patna. Okay, so first of all, overview. So this week's lectures were focused on flexible nonlinear system. So the lecture started with how uh, the rigid structures are and what are the need, and why do we actually need a flexible nonlinear system. After that, various types of flexible linear systems like that of a cantilever beam. It was discussed, different type of cantilever beam, like for example, the base excited cantilever beam, parametrically excited cantilever beam. It was discussed, and apart from that, various types of cantilever beam, like for example, if I want to have a elastic cantilever beam, or if I want to have a viscoelastic cantilever beam, or maybe the magnetically stimulated beams like that were also taken care. And apart from that, sandwiched beams were also discussed, that how sandwiching of different materials would help us to get the property that I want for a particular system. Okay, and after that, piezoelectric energy harvesters were also discussed. So, piezoelectric energy harvesters are basically used for harvesting energy from vibration systems. So, as we know that a piezoelectric system is actually shows a direct and reverse piezoelectric effect, and because of this kind of property, what do we do? We can use this piezoelectric material in order to harvest energy from the vibrations. Okay, so these three things were discussed. So now I'll be taking up the questions. Okay, I hope that you people have gone through the lectures. Okay. Now coming on to question number one, the disadvantage of a flexible system is. First of all, what is a flexible system? And even before that, what is the use of a flexible system? Why was flexible system even introduced? Okay, so firstly, we'll talk about what is a rigid system, right? Because up till now we were discussing about rigid systems, isn't it? We were discussing about rigid system. Now, but if you remember the basic definition of rigid system, which upon which the engineering mechanics is based, is says that upon the application of force, the rigid system does not show any type of deformation or change in the shape and size of a particular body. Also, the like if you remember, suppose this is a body A. It is kept on a floor, and now apply a force F on it. Okay, so what is going to happen? The body is going to move to a new position over here, A. And let us suppose that it is at a distance x naught from the initial reference. Okay, so we say that the body is the same, it is having the same volume, it is having the same dimensions, it is showing no deformation. And if we consider 2 points, let us say these 2 points, A and B, And then again see these 2 points A and B. After I have applied force, what do I see? I see that the distance between these 2 points remain the same even after the application of the force. So I say that my body is a rigid body. Correct? So this is how we define rigid body, and my engineering mechanics is actually based on the rigid bodies because I don't assume that any kind of a deformation is actually happening in the body. Okay, so I can say that it does not change, yeah, or I'll just write it does not show deformation on the application of force. Cool. I guess this is clear. Okay. Now, if I talk about, so this is a theory, right? If I talk about a physical system, is it possible? Is it practically possible that the body is not going to show even infinitesimal amount of deformation? See, that is not possible. So, how do we differentiate? So we say that any body which shows the minimal amount of deformation, or maybe we would say up till a certain 1, 2, or maybe 5% of its dimension it is showing deformation, less than that, then we can say that it is a rigid body. So we'll just conclude that a body that shows minimal deformation on application of force. Okay, so this would be my rigid system. Now as the question is about a flexible system, so first let us discuss about the disadvantages of a rigid system. Now, what are the disadvantages of a rigid system? See, if I am saying that my system is having very less deformation, so what does it mean? It means that it is having very high stiffness, isn't it? It is having a very high stiffness, that is why it is not showing any kind of a deformation in it, right? And if it is having a very high stiffness, then it means that it must be heavy. You just write disadvantages, rigid system. Right, so what would I write? I'll first write that it is heavy. Now, if anything is heavy, carrying it is definitely a difficult task, right? You know, these metals that are being used for various constructions or for making various kind of devices, so it is very heavy. Why? Because of the presence of metal. Correct, because of the presence of metal. Right. For example, if I have this bottle, it is made up of metal. So if I remove all the water that is inside it, it is having some weight, right? And that weight is high if I compare it with a plastic bottle, right? So it has weight. So this is just an example. Likewise, you can consider other things also, right? Like now, like previously, we used to, in case of certain applications, if I have a motor or if I have a gear mechanism, and it is preferable that it is shaded, it is closed in a box, right? So people used to make the box of metals. It was heavy. Now we are in a generation of 3D printing, right? So we can make those boxes of plastic by 3D printing, right? And definitely plastic is much lightweight, right? We like take the example of rubber, it is also very lightweight. So it is heavy. Then it has now if it is heavy, then it is having more mass. If it is having more mass, it is going to have more inertia. Correct? Because eventually inertia is because of the mass. So it will have high inertia effect, correct? Now, if it is heavy, it is having high inertia effect, definitely it is going to consume more power. If I talk about a application where we involve, like for example, if I talk about a well, right, which is used to take out water, right? Now, if I have a bucket which is made up of metal, right, and I use a pulley mechanism to take out the water from it, right, and I consider that the amount of water would be the same for the case when the bucket is of metal and when the bucket is of any, let us say, other material. So if the metal bucket I'm using to pull out the water, and I'm actually using some mechanism, some machine, in order to take the water out of the pulley, so what is going to happen? It is going to take more energy. It is going to consume more power, correct? As compared to the other material, let us say of that of, if I take a bucket of plastic, right? Because it is going to have lesser weight. So definitely it is going to consume more power. So consume more power, right? Then now since it is heavy, it is having high inertia effect, it means it is going to be slow, isn't it? It is going to be slow. Its effect is going to be slow. For if I apply a force on it, because of its inertia, it is going to move slowly, right? So it is slow, slow movement. And then we require more time. We require more time for fulfilling a task. Like for example, if I give, if I have a system which has a more mass, if I have a system which has less mass, I want to do some kind of a work on it. Like if I want to lift both the bodies, and I am giving the same power to both, right? But the energy consumption for a heavy body will be more as compared to a low body. So definitely the heavy body is going to take more time, right? So more production time, or let us say more productive. Apart from that, there are also several disadvantages of rigid systems. Because see, when we are saying it is a rigid system, it means that it is heavy enough and it is stiffer enough. Because see, I told you the definition. Like I assume that around 3 to 4% of its length or dimension it is going to deform maximum. So it means that it is going to be heavy and it is going to have very high stiffness so that it fulfills the criteria of being a rigid system. Okay, so even if I am considering it as a rigid system, it is going to have several disadvantages like high inertia, more power consumption, more stiffness. So using it for intricate operations and very tedious operations would be very, time consuming and very expensive as well, isn't it? So this, and also I'll give you an example. If I talk about a crane, which is used in the making of buildings, so can a crane lift uh, the amount of weight as itself? Definitely it cannot. It has some limitation up to which it can lift the load. However, if I talk about a human muscle, or if I talk about humans, we are made up of muscles, right? And we are a very complex system. But you see that if you try to start lifting 1 kg every day for, let us suppose, 10 day or 20 day, after 20 days you'll feel that now I can lift 2 kgs, then 4, then 8, then maybe I'll keep increasing up to some amount, right? So if you see that a human body, though it is light in weight, correct, it is more deformable, it has less stiffness as compared to the heavy metals, then also it is able to do a high amount of work. It is going to lift the body and everything, right? So why is this happening? And why cannot we have an alternate other than these rigid bodies in our life so that it also operates like that of a human muscle, right? It would actually reduce our effort. right? So that is why flexible systems were introduced. So when I talk about a flexible system, I define a flexible system as first, which does not satisfy the criteria of rigid system is a flexible system. Second, if I talk about what flexible system is, so a system that deforms on the application of force on it, right? So this is my flexible system. Now, if I talk about a flexible system, what are the advantages of a flexible system? What do you think? Definitely, the disadvantages of the flex of a rigid system, the opposite of that is going to be our advantage, right? But if I talk about, okay, first let us slide the advantages. Then we'll go on the disadvantage. Definitely, everything has its disadvantages as well. So I'll write about advantages. It is low weight, then it is going to have less volume. Okay, then it is going to have low power consumption, definitely, because the inertia effect is less, so the power consumption is also less. We can write less inertia. Okay, it is cheap. Definitely, it is cheaper. If you go to purchase rubber, it is cheaper than purchasing a metal, right? It is cheap. And apart from that, if I talk about the logistics and everything, like if I want to transfer a metal from a place A to B, it is going to have a high transportation cost, while a flexible material is going to have a low transportation cost because it is flexible. I can make its bundles and transport more amount from a single truck as compared to the rigid system like metal. Okay. But despite having such advantages, there are certain disadvantages of a flexible system as well. Now, what are those disadvantages? So the disadvantages include first, since it is having lightweight, it is actually having less inertia effect, definitely it is going to have low stiffness. Disadvantages of flexible system. I have low stiffness. But why is low stiffness a problem? The reason that low stiffness is a problem is the system becomes inaccurate because of it. The system becomes inaccurate. Now, see, for my rigid system, it was only able to deform 4 to 5%. Now, when I'm saying it is able to deform 4 to 5% upon application of very high amount of force, it means that the deformation for a very small amount of force is very less. Like if I try to plot it, if this is my force and this is my displacement. Okay. So for a rigid system, it is something like this. The slope is very steep. If I talk about a very small amount, I'll just make another curve to show you an exaggerated view. Something like this and something like this. Let us suppose that this is my rigid and this is my flexible. And let me talk about a very small amount of deformation. Okay. So if you see over here, the delta F for rigid is having a certain value. Well, if you consider over here, the delta F flexible is a very small quantity. So for a very small amount of displacement, my rigid body is having a very high, is requiring a very high amount of force, while my flexible body is having a very small amount of force is required. Now, if you see that if the very small force is required, if I am applying a force, see, there is always an error. There is always an error in a physical system. Right. So if my flexible system is actually actuated for a very small amount of force, even an error of very small amount in the force is going to lead to a displacement which is different from what is required. Despite the fact that I'm giving the amount of force which is required, it is going to show the displacement other than what should it be. Why? Because of the error in the force. And it could be possible. It could be due to many different reasons, due to the human error, due to the error of whatever the system we are using to apply the force, anything. It is very common, right? So it makes the system inaccurate. Okay, so this figure is an exaggerated view. This is just for an example. However, the rigid body, in case of a rigid body, the line should be like this, straight line, vertical straight line. Okay, this was just to make you explain, make clear what I am trying to say about inaccuracy. Okay, so this my system is inaccurate. Now, if I talk about, okay, my system is inaccurate. What if I try to control it? Why do I apply control? I explained in the earlier sessions also that I try to apply control in order to basically control this output of my system. I'll apply a feedback loop and I'll try to give my system an input which is required to get the desired output. But now this system is difficult to control as well. Why? Because of the error. If you know, if you have studied about control system, any kind of a controller actually works on the error. Error which we define by taking the difference between the reference and what is actually response of the system. Reference minus the actual response. So what is it? It is the error. It is defined as the error. What if this is very small? If this is very small, then again a very small variation of force is going to happen. Any kind of an error in that is again going to make the system inaccurate. So, a very advanced control system, a very advanced and a very accurate control, very precise control system is required in order to control these kind of flexible systems. So, it is difficult to control, right? It's difficult to control. Also, we can also use the mathematical power or mathematical power in order to model the system. But if you'll see that for a flexible, like if I talk about a rigid system, what did I say? I say that it is going to show deformation for a very small amount, right? And in the initial lectures, if you have studied, and as I've also talked in the live session as well, that any kind of a physical system can have a linear behavior up to a certain amount. Any kind of a physical system may show linear behavior up to a very small amount of deformation. Correct? Now my rigid body is showing no deformation or a very small amount of deformation. What does it mean? It means that my rigid system is going to have a linear behavior. So if my rigid system is going to have a linear behavior, I'm going to have a linear relation in order if I try to model the rigid system. While in case of a flexible system, I know that my flexible system is going to have low stiffness and it is going to be very fast in deformation. So definitely it is going to operate outside of the nonlinear zone. Though I agree that we can actually limit our analysis for the linear zone, but the linear zone is very small in case of a flexible system. Correct. It is going to go into the nonlinear zone. So if it is operating in a nonlinear fashion, if I try to now model it, definitely its mathematical model is going to be complex because it is going to involve nonlinear terms. And the introduction of nonlinear terms makes difficult to form a closed form solution, and then predicting about how the system is going to behave becomes difficult. So one of the disadvantages is also that complex mathematical model. So these are some of the disadvantages of the flexible system. Correct? I hope that what I'm trying to say is clear. Okay, now if I come to the question, the disadvantage of a flexible system is inaccurate position. Correct? Complex, yes. Small volume. Do you think that small volume is a disadvantage? No, small volume is not a disadvantage. It is in fact a advantage. It is having a small volume, which means that carrying it from one place to another or the effort that is required in order to actuate the system would be less and fast. No, this is also not an disadvantage. It's an advantage. It's another advantage that the system is fast. Okay, so the above two are going to be the disadvantage of the flexible system, and I hope that it is clear to you people that how the system, flexible system is, what are its advantages and disadvantages, and why what was the need to actually introduce flexible systems. Now, question number two, the problem encountered for flexible system may be avoided by. Okay, so if you remember that what are the problems of a flexible system? So first problem was that it is inaccurate. Then we had, yeah, low stiffness. And since it was inaccurate and it had low stiffness, it was difficult to control. And then we had complex mathematical model. Now the question is asking that the problem encountered, how can we avoid? How can we try to avoid so that I can see our rigid system was also having some disadvantage, right? My rigid system was also having certain disadvantages. However, I was using my rigid system. I was using the rigid system for various application, right? So after looking into the disadvantages, we tried to look into the flexible system. Now my flexible system is also having disadvantages. So I need to find out certain ways by which I can control these disadvantages. I can at least nullify its effect, right? So the best way is to apply control. But in order to apply control, I need to have what? I need to have control strategies that are very precise and accurate. Correct? That should be very precise and accurate. So, control of flexible system. Now, the control of the flexible system is actually divided into two categories, passive and active. Okay. So, if I talk about a passive control, what do I mean by it? So see, if you remember the spring mass system, the spring mass system was, if I give it some kind of a initial condition, it is going to vibrate. If I'm going to apply some forcing frequency on it, it is going to vibrate. Correct. So these are some properties of the spring mass system. However, if I introduced a damper into the system, spring mass damper system, any kind of a small vibration, if it was small initial vibration or initial condition, it was given to the system. My damper was actually helping to reduce the vibration and to take the system to its equilibrium state. So what was it doing? It was actually controlling my system. It was actually making my system stable. Correct? Now, if I talk about forcing, so in case of forcing, I saw that if my system was not having damping, it was actually vibrating with presence of two frequencies, which was my natural frequency and the forcing frequency. And if it may happen that my amplitude kept on increasing or it was constant, okay. But I wanted to have a amplitude lesser than what was the system was possessing. So if you remember that if I introduced a damper into the system, firstly, my component of vibration, which was due to the natural frequency, it was damped out. Secondly, the amplitude due to the forcing of the system was reduced because of the introduction of damper, correct? So what was my damping actually doing? My damping was passively controlling my system. My damping was actually stopping my system to go to any kind of a failure, any kind of a high vibrations, right? So my passive control of flexible system includes viscoelasticity. Now you'll ask that what is viscoelasticity? We were talking about dampers and everything. So see, viscoelasticity, what does it mean? If any kind of an elastic body, if you see, if you try to stretch it first take a metal, try to stretch it. It is very difficult to stretch it. But if you take a elastic body and you try to stretch it, what do you observe? You observe that it is easy to stretch it. Like you take a rubber band and stretch it, it is comparatively easy to stretch it. So what happens is that those kind of a system actually possess some kind of a viscoelastic behavior. You know that in case of fluids, we have this viscosity, right? So we say that the elastic systems has viscoelasticity. Okay, so it has some kind of a presence of a viscous effect, right? So viscoelasticity, if it is present in the system, what is it going to do? What is it going to do? Definitely, it is going to give some amount of a damping to the system, correct? It is going to give some damping to the system. It is going to give damping to the system, correct? And as we saw it in the spring mass damper system, that my damping was actually acting as a control, passive control towards my system. So here viscoelasticity is going to provide some damping, and that damping is going to give some passive control of the system. Now you would say that how can I vary the viscoelasticity? So it depends. See, when you are actually manufacturing a flexible system, how you are going to add the filler particles into it, how you are going to take the medium, what kind of a medium you are going to take. Based on that, you can change the viscoelastic property of the material. Okay. Then, if I talk about more, then we can have various other ways also of passively controlling the system. Like we had tuned mass dampers, which we discussed earlier. Tuned mass dampers. Remember when we had a single spring mass damper system and we introduced another spring and mass to the system in such a way that if my forcing was given to the primary system with a frequency equal to omega 2, which was actually the natural frequency of my secondary system, then only my secondary system is going to oscillate and my primary system is going to show no oscillation. So what we were calling it tuned mass damper. We were saying it tuned mass damper because we were able to tune the system. So that is also a passive control system. And likewise, we can use sandwiched structures. Now, when I say sandwich structures, what I mean is that when I am actually making a beam or when I am actually working on a material, what I can do is I can make the material something like this, wherein this is my core. My core could be soft and my outer part can be hard. So what is going to happen? These kind of a material is going to show property of both hard and soft material. My soft core is going to show some damping properties and my hard core is going to show the rigid body's property. So it is going to behave in both ways. And then the amount of thickness which the hard part should be given and the soft part should be given. What kind of a material should I choose for a hard part? What kind of a material should I choose for the soft part? It would depend upon that what is my application. Okay, so it would depend upon the designing, right? And the designing is based on the application, right? So these are some passive. Now we call it passive. Why? Because it is not being actuated by some external stimuli. Now, likewise, we can have some active control also. Now, what do I mean by active control? Now, by active control, I mean my MR based elastomer. If you remember, I told you that my MR based elastomer, which is basically magnetorheological based elastomer. So this my magnetically rheological based elastomers, they have the property that if I change the magnetic field, like for example, my system is just kept like this without any magnetic field, then it will be having some deformation, it will be having some properties, material properties and everything. Now, as soon as I apply some magnetic field, what is going to happen? It is going to show change in the deformation, and it is also going to show change in the properties. And by varying the magnetic field, I can change the property and I can just get whatever amount of the property and deformation I want from my system. Okay, so these kind of materials are known as active, and such control can make, like if I make the system, my flexible system is made up of MR based elastomer. So then whatever the amount of stiffness I want, whatever the amount of this deformation I want for my system, I can control it depending upon the magnetic field that I apply. Likewise, I can have piezoelectric patches. I can have piezoelectric based materials. If you remember piezoelectric materials, they show deformation on the application of electric field, or when they deform, they have charge on itself. It shows both the direct and the reverse piezoelectric effect. You can also consider electroactive polymers, which are actually based on piezoelectric materials only. The only difference is that the electroactive polymers are only going to show the reverse piezoelectric effect. Okay. So by these methods, I can actually control the system. And if I'm able to precisely control the system, if I'm able to introduce some amount of a damping, if I'm able to increase or decrease the stiffness of the material depending upon my application, then definitely I can avoid whatever the inaccuracy and low stiffness problem that I was encountering in case of flexible system. Apart from that, mathematical modeling can also help me. Now you would ask how? Because it was, as I told you, that it is complex since it will be nonlinear. But then if you'll ask that how can mathematical modeling help? So that is what we have been doing since the last 10 weeks. That is what we are doing since the last 10 weeks, isn't it? We are doing mathematical modeling. We are actually dealing with the nonlinear system. We are actually learning that how should we deal with the nonlinear system in order to get the accurate result, so that I can study how my system is going to behave, and I can then use it for the practical application. And that is why studying of nonlinear dynamics is very essential, because if you want to deal with flexible system, if you want to reduce your power consumption, if you want to reduce your time, if you want to make your life easier, you have to work on flexible systems. If you'll have some flexible alternative, then it will be very helpful, isn't it? Like for example, every one of you wears watch. Right. What if that watch was made up of some metal? Will it be comfortable? Will you ever wear it? It will not even give a fashion statement. And comfortable so it is never going to be. But if you see that our straps of the watch are either made up of some kind of a rubber, or if it is even made of metal, it is made up in such a way such that it is able to cover the whatever the shape of our arm is, and that too in a very comfortable way. So that is why studying flexible system is important. And if you want to study flexible system for complex dynamical systems, it is very important that you understand how we are supposed to deal with the nonlinear system. So in this case also, you can use mathematical modeling. Get the nonlinear differential equation. And then what is required? Once you get the differential equation, use the method of multiple scale, use the method of perturbation, use any other method that you want to get what kind of a solution it is going to get. Use the Floquet theory to find whether the system is having a periodic solution, a stable or unstable periodic solution. Use the numerical technique in order to know what the system is going to behave when wherever the method of multiple scale or wherever these kind of a method is not going to operate. It makes your life easier. Right. So the answer to this question would be all the three options A, B, and C. Mathematical modeling, it is going to help you, right? Because it will help you to get the equation of motion, solve the equation of motion, and then you can get whatever the system is going to be. Just solve it numerically, analytically, whichever fits your requirement, depending upon the application. Okay, then passive control by changing the material properties, by changing what value till of the viscoelasticity you want, by using the tuned mass dampers, by using the sandwich structures, by choosing that what kind of material should be used in order to produce a sandwich structure. And third is by active control, which includes MR-based elastomers, piezoelectric patches, use of a material that can actuate based on the external stimuli. Okay, I hope that it is clear. Coming on to question number 3. Okay, so this question was just for a revision. If I remember, this was also discussed in the earlier live session also. So the generalized Galerkin method is used to option 1 to convert the second order differential equation into first order differential equation. No, to convert spatio-temporal equation into temporal equation. This is the correct option. Now, what is a spatio-temporal equation? A spatio-temporal equation is an equation which consider both variation with both space and time. Variation with both space and time. And my temporal equation is going to have variation with time. Okay, so variation, if we have variation with both space and time, what is going to happen? If you remember that there are two kind of differentiations. One is your differential, ordinary differential, and second one is your partial differential. Do you remember? If my f is a function of t, then its differential I can define as d of ft by dt. I use d. While if my function is actually a function of x, y, and t both, then if I want to define its differential, how do I do? Then I define its differential as, if I want to differentiate it with respect to time, then I use partial differential. I use partial differential. In case of a partial differential, in the equation I consider that my x and y are treated as a constant, and then I differentiate only with respect to t. So if I'm considering the variation with both space and time, what is going to happen? My equation is going to have differentiation with time, and it is going to have differentiation with space. Now my space is three-dimensional, x, y, z. So I'm going to have four kind of a differentiation, which makes my system PDE, partial differential equation. Now if I have a partial differential equation, it becomes a bit difficult, right? Because in partial differential equation, we are actually focusing on the variation with space and the variation with time, right? Which means that how my system is behaving with space. If I have a box, if I have a small, let us say if I have this kind of a plate, this kind of a plate I'm having, and if I'm this kind of a plate, then what is going to happen? So I'm going to see that with how deformation occur with time first, and second I'm also going to see that whether how the deformation is in the space, in the x, y, and z direction, right? I would like to see that as well. Okay, I'm assuming that when I talk about a spatiotemporal equation, I know that now my variation with x is not the same. The thickness is not going to be the same. The length is not going to be the same. It may happen that my system is, after deformation, it's going to have something, this kind of a behavior. After deformation, instead of this, it is going to be this. Now, if I want to incorporate the variation in the thickness as well, what would I do? I'll go to a spatiotemporal equation, wherein I'll consider variation with both space and time. And if I want to do that, what is going to happen? It will make my system a partial differential equation. Okay, so your generalized Galerkin method is basically making your life easier because it is making a partial differential equation converted into ordinary differential equation, because now the variation is only with time instead of considering the variation with space and time. Clear? Okay. Okay, now coming on to question number 4. Vibration is which kind of external energy source? Now, if I talk about energy source, what is it? What is my energy source? All of you know about solar energy, wind energy, tidal energy. We all know, right? So, if I am having some amount of solar energy with myself, what am I supposed to do? What are we actually doing? We are actually using that solar energy in order to make our lives easier by producing electricity, by charging batteries, right? We are using it. Likewise, we can use wind energy. We can extract energy of the wind. Now, because these are all, these are all renewable resources, right? Nature is giving it to us. Now we have renewable and non-renewable resources, every one of you know, and you know that the non-renewable resources, they take a very hell lot of time to get produced, and that is not available in abundance in the environment, right? So we are switching towards renewable. So here we'll be talking about renewable only. So if I talk about renewable energy source, I have sunlight, I have wind, I have tides. So I can use these to generate energy. And from that energy, now when I'm saying energy, it would depend upon mechanical energy, electrical energy, or whatever kind of energy I want for any kind of a production. Like for example, I can generate it electrical energy, right? And then I can supply it to the people, right? So now this is further divided into two categories: high level, low level. Now, why high level, why low level? So, see, as an engineer, it is my aim that I harness every possible energy that is being wasted in the environment. Okay, to make the ecosystem balanced, right? So, if I'll categorize the sources of energy on the basis of high and low, then I can prioritize. Correct. For the high level, what I can do, I'll have high energy, I have high capacity, I'll get high intensity of energy, so I can maybe use it to power a house. But if I'm having a low energy source, which means I'm going to have a low capacity, I'm going to have low intensity of energy. So should I just leave it? Because it will not be able to power the whole building. But leaving it like that would not be justice. So what will I do? I'll just harness it also and maybe use it for operating a particular equipment, or maybe charging my battery, or maybe charging my phone, charging my laptop, or I can use it for all out, which is used for killing of the mosquito. Anyways, I'm saving some amount of energy. And if everyone tries to save a small amount of energy through this, we can actually save a lot of energy, right? So that is why it was characterized that we'll just divide energy source into two categories, high level and low level. So then we can prioritize what kind of energy should be used for what kind of an application. So in high level of energy, firstly, what are the high level of energy source? So it has high capacity or high intensity of energy produced. So definitely if it has high intensity and it has high capacity, it will be used for large scale. And as an example, you can have your solar, wind, tidal. Now, don't compare it with the non-renewable energy. Every one of you know non-renewable energy is going to produce more energy as compared to your solar, wind, and tidal. But here we are only considering the renewable part. Okay. Now, if I consider low level, low level, it means that it is going to have low intensity or capacity of the energy produced. Right. So in that case, where are we going to use it? Definitely we are going to use it for small scale. And what are the examples? Examples are heat. Examples are heat. Now by heat, I don't mean thermodynamical heat. By heat, I mean if you are boiling a water, some amount of heat is getting out of that water, which is being wasted to the environment. Use that heat, that amount of heat. Okay. So we'll have heat, we'll have noise, and we'll have vibration. Noise, noise, cars produce noise, and various construction sites they produce noise and everything. So what is noise? Noise is essentially the vibration of the air that is around us, isn't it? It is because of that only. So maybe the vibration of those air, we can use it in order to convert it into a energy, right? Usable form of energy. Then we'll have vibration like machines when they operate and many different kind of machines, they produce vibration, which is actually excess of the energy. And you'll notice that that is not actually required. That is not the work of the machine that it is supposed to do. But whatever the energy that is being generated because of the vibration or because of the heat produced or because of the noise in those machines, the energy is getting lost, which is why the efficiency is being reduced. But that is something we cannot actually just avoid. Okay, we try to avoid as much as possible, but that is not at all, we cannot make it to zero. Correct. So in that case, what we can do is instead of just letting it to get wasted, we can use it. Like I told you that piezoelectric material has the capacity that if I deform it, it is going to produce voltage. It is going to produce charge, right? So if my one of my machine is actually vibrating, okay. So what can I do? I'll just apply piezoelectric patch on it and I'll just connect wires in such a way such that charge can flow. And then I can so store the charge maybe inside a battery or something, or I can just try to, like for example, it has a meter which measures the speed of the machine and that it is showing it through the digital display. Now, if the digital display it requires power, so what will I do? I'll just apply a piezoelectric patch. I'll connect it to the digital display. Now, my digital display does not need the electricity. Now, my digital display is actually operating because of the vibration, extra vibration that is produced by the machine, by which my energy was actually getting lost. Now, I'm using it in an accessory. Okay, so I've increased my efficiency. I've reduced the power consumption, though by a small amount, but using these small amount can actually increase the efficiency. Correct? So this is the concept of low level energy sources. So as the question says, vibration is which kind of energy source? So it is a low level energy source. However, we can use it in order to produce energy which will be further used for the charging of some small appliances or operating of some small appliances, etc. Likewise, noise, you can also use noise that are being produced by machines. We can actually take the noise, we can take whatever the energy is being lost by the noise, and then we can operate some other small equipment through it. And that comes with the heat as well, right? Like for example, in case of heat, if you know about the operation of a thermal power plant, a lot of a lot of heat is being lost in it, right? Because whenever you are actually burning the coal, first the coal is being converted into powdered form and then it is being burnt and then the energy is used. Like if I talk about a supercritical boiler, it is used to convert water into your steam, and then the steam is used for the working of a turbine. So not all the amount which is being heat that is being produced by burning of a coal is used to increase the temperature of the water. Some of it is lost in the environment as well. So what we can do is we can actually utilize the heat that is being lost in the environment, which is also resulting in the increase of the temperature of that place, right? And it makes very worse for the workers to work over there. So we can actually use the excess amount of heat which is being lost in order to operate some kind of a equipment or in order to store that energy, right? Now comes question number 5. Which of the following are the type of piezoelectric energy harvester? Now, firstly, what is a piezoelectric energy harvester? As I told you, my piezoelectric material has two kind of a effect. First is the direct piezoelectric effect, and second is the reverse piezoelectric effect. Now, if I talk about the direct piezoelectric effect, it means that this is my piezoelectric patch, and if I deform it, something like this, it is going to possess some charge. Okay, this is produced in the material because of the deformation that I gave it to it. And then I can just take this charge out and store it or maybe use it. Okay, so this is how energy is harvested to piezoelectric energy harvester. So the question is that how is it actually working? Okay, so for example, we have a wind blowing. Okay, and like the example that has been discussed in the lecture of nonlinear dynamics as well, if I talk about a cantilever beam, and suppose the wind is blowing in this direction, what is going to happen? This cantilever beam is going to bend like this. And then if I have a bend like this, then it is going to again go like this. What is going to happen? This beam is actually going from one place to the other. It is vibrating, correct? Now, if I apply a piezoelectric patch over here, something like this. So you'll see that it is actually deforming with the beam. Firstly, it was in this position. Now it has changed to this position. It has changed its thickness or maybe whatever the length is. Okay. So now since it is showing some kind of a deformation, what does it mean? Since it has now shown some kind of a deformation, it is going to now possess some charge around it. And we'll just harness that charge, send it to the storage and store it, or maybe power the appliance or whatever we want to do with it. We can do it, right? So this is how energy is harvested through the piezoelectric material. Like I have given one example, you can have multiple examples, multiple examples. Okay, so your piezoelectric energy harvester are classified A, linearity. So as I told you, I have the option, right? And depending upon the application. So if my application involve very small deformation of my piezoelectric material, or at least deformation which is inside the linear zone of the material, then I can say that my material is behaving linearly. While if it is having very large amount of deformation, then in that case I can say that my system is behaving non-linearly. So on the basis of linearity, on the basis of what amount of deformation my system is going to have, I can classify my piezoelectric harvester into two categories, linear, non-linear. I guess this is clear and this is very simple. Linear and non-linear. Operating in the linear zone. Or we can just write large deformation. Okay, linear, not linear. Then I can classify it on the basis of mode. If you remember mode, where mode was discussed. So if a system is having 1 degree of freedom, it is going to have one natural frequency. But if my system is having 2 degree of freedom, it is going to possess two natural frequencies. And if my system is actually oscillating in the first mode, it is going to show some different kind of a variation. And if it's going to vibrate in the second mode, it is going to show some different kind of a vibration. So on the basis of mode, it can be single mode or multi-mode. Now, how is it my choice, single mode or multi-mode? So see, if I consider my system as a single degree of freedom system, I'll have a single mode. If I consider my system as a 2 degree of freedom system, I'll have two modes. And if I consider my system as a continuous body, which is it actually is, it is going to have infinite number of degrees of freedom, which means that it is going to have infinite number of natural frequencies. And in that case, it is going to be a multi-mode system. Correct? Multi. Going to have 1 omega n, and here it is going to have multiple resonance frequency. I hope that this is clear. Now, coming on to the third basis, internal resonance. Do you know? Do you remember what is internal resonance? Okay, so the case of internal resonance, it is going to be with internal resonance or without internal resonance. If my system is multi-mode, then it is going to be with internal resonance, because internal resonance is going to occur if my system is having multiple modes. For a single mode, it is not. So with, if it is having multi-mode, and without, if it's not having multi-mode. Now, if you remember what is internal resonance, in case of internal resonance, what happens is that your multiple natural frequency, multiple resonance frequency synchronize. Okay, multiple natural frequencies of system are going to synchronize, that too under certain condition. And what is this going to do then? So then it is going to produce an effect at a frequency other than the natural frequency. Or else should say resonant resonance frequency. So what happens is that, okay, my system was having one frequency, let us say 3 natural frequency, and one was 5. So if I used to give it 3, it was going to have very high amplitude of oscillation. If I used to give it 5, it was having very high amplitude of oscillation. But there was also a case wherein these frequencies were synchronizing, and maybe I'll say at 2.5, at a frequency equal to 2.5 also, it was showing a very high amplitude resonance. So this is when internal resonance comes into picture. Okay. So it is very important that in case of a multiple modes, we consider the effect of internal resonance in order to avoid any kind of a failure of the system. And then D is on the basis of excitation. So there are various types of excitation, isn't it? So one will be your direct excitation. Second could be your parametric excitation. Third could be your random excitation. And fourth could be your simultaneous excitation. Direct excitation, you know F sin omega t. Forcing is applied on the system. Parametric excitation, Parametric excitation means that any of my parameter is actually dependent on time. Any of my system parameter is actually dependent on time. And then comes the random excitation, wherein the excitation is not necessarily a function of sine or cosine. It could be random, like the wind blowing. It is not necessarily a sine or cosine function. It could be random. Wind can blow randomly, right? And third is your simultaneous. Simultaneous means two kind of a vibration is imposed on the system. Okay. So any these kind of a way, any of the class in the basis of classification of these, I can say what kind of a my energy harvester it is. It could be a linear energy harvester. It could be a non-linear energy harvester. It could be a single mode energy harvester. It could be a multi-mode energy harvester. It could be a internal resonance energy harvester. It could be a without internal resonance harvester. It could be a parametrically excited energy harvester. It could be a directly excited energy harvester. It could be a simultaneously excited energy harvester, or it could be a randomly excited energy harvester. Any of the form it can take. It can have multiple things also. Like it could be a simultaneously excited multi-mode nonlinear energy harvester. Energy harvester which is behaving nonlinearly, which is having multiple degrees of freedom, and which is excited simultaneously. All the three things. Okay, so these are the types by which I can actually define how which kind of a my piezoelectric energy harvester is. See, it would depend now. Like if I, as I gave you this example, that I'll just keep it in the wind. Sorry, that if I keep it in the wind, what kind of a energy harvester do you think that I should have? If I'm keeping it in a wind and if I'm considering all the weather condition in a year, so it could have a summer day with a very high speed of Lu, or it could be a winter day with no air or with no wind, and it could be a rainy season also. It could be some you can say some kind of a windy environment wherein the wind blows at a very high speed, or someday it could have no speed, many options. So what I know is that my system could have a very high amplitude, so I would design it as non-linear. Then my system is continuous, so I should have multiple modes. Then my system could be randomly excited because my wind is not necessarily going to have a certain kind of a function. So it could be randomly excited and it will have internal resonance. So in that case, I'll design my piezoelectric energy harvester as a non-linear multi-mode with internal resonance and randomly excited type of piezoelectric energy harvester. I hope that this is clear. So in this case, first option is correct, second option is correct, fourth is correct. This should also be correct. Here I have missed writing internal. Okay. Okay, now coming on to question number 6. So it says that write the constitutive relation for the piezoelectric material. So first is, what is a constitutive relation? Why is it even required? So by constitutives, if you remember, we had this Hooke's law for metals, isn't it? Where we define Young's modulus. We say my stress is directly proportional to strain. Remember, that was also constitutive relation. Likewise, my elastic material should also have a constitutive relation. Otherwise, how am I going to model it? How am I going to actually find the equation of motion? So I should have a relation which could relate my system. So I'll have a constitutive relation. So what could be my constitutive relation? So if I talk about a piezoelectric material, if you remember, my piezoelectric material is going to have both the effects. One is direct piezoelectric and the second one is going to be inverse piezoelectric. correct? In direct piezoelectric, what was happening? In direct piezoelectric, I was actually giving deformation and my charge was getting produced. In inverse piezoelectric, the reverse was happening. I was giving charge and my system was actually showing deformation. Okay, I know this now. Now, if I try to find a relation, how is my system going to behave? So we define in case of a piezoelectric material two things. One is my strain, you people are familiar with it, and second is my dielectric displacement. You can consider dielectric displacement as an analogy to strain, and it is basically used for dielectric materials. It is basically signifies how my charge or basically how my dipoles are actually moving inside the system. So in case of my piezoelectric material, I have two relations. Okay. My first relation says that my strain S is written as D into E. E is my electric field. S is my strain. And what is my D? So D is being defined as my piezoelectric strain constant. If you closely look into this equation, what is it actually telling? It is saying that my strain is actually related to my electric field and it is proportional to it. So if my electric field is increasing, my strain is increasing, which is correct also. If I increase the electric field, it is going to show more deformation. Correct. And these were introduced as my proportionality constant, I can say. Similarly, if I talk about my electric displacement, I can write my electric displacement D as small d into capital T. Now T is my stress. Now you would say that what is this? So your first equation, if you see your first equation, what is it telling? It is telling that how if I apply the electric field, my strain is going to change. So it is actually what this is a mathematical form of your inverse piezoelectric effect. So there should be a relation of my direct piezoelectric effect also, wherein if I apply some amount of a pressure onto the material, it is going to show different change in the electrical properties of the system. It will show the movement of the charge. It will show my dielectric displacement. And this is my that equation. This is for direct effect and this is for reverse effect. Correct? I hope it was very clear. Now, apart from this, let us for now forget piezoelectric material. Let us come to an elastic material. So, an elastic material and an electrical equation. So, apart from having a piezoelectric effect, my material is also having some by nature effect. My material is elastic. So, definitely I am going to have a stress strain relation. Na? Definitely I am going to have a stress strain relation also. So, if I talk about my stress strain relation, what should it be? It says that my strain is equal to some small s into T. T is my stress, capital S is my strain. Strain is equal to small s into T, strain. This is my elastic behavior. And other than that, okay, I cannot write it here. I'll have to explain then. I hope that it is clear. I don't have to mention it. And apart from that, I'm going to have electric effect also because of the electric field that is applied on the material. So in that case, I can write my dielectric displacement as epsilon into electric field. This is for a material, capacitive material. If I apply electric field, the charge is going to move. And this is defined as that. Now my piezoelectric material, it has the capability that it is going to behave as an elastic material also, and then it is going to show some electrical properties also. So what should there be? There should be both the effect of your electric field and stress on the strain, and the effect of electric field and of the stress on the dielectric displacement. Correct? So what am I going to do? I'm just going to add plus d to t. Now this gives your constitutive relation. For the reverse effect, wherein my strain is actually depending upon both my stress as well as my electric field, which is correct for a electroelastic material, and then my dielectric displacement is going to depend upon the stress as well as the electric field. I hope that this is very clear. Now, there is two things that should be kept in mind. First, your S is, sorry, okay, epsilon, I know, I think you people know, it is the permittivity. Dielectric permittivity, and it can be written as epsilon naught into epsilon r, where epsilon naught is your permittivity and epsilon r is the relative dielectric permittivity, right? Epsilon naught is your actually permittivity of the air, and then you have your small s, right? Where what is your small s? You can say that it is the elastic compliance for now. I hope this is clear to you all. Okay, so one thing that you have to remember is that your elastic compliance is always measured at a constant electric field. Elastic compliance is always measured as an at a constant electric field, and then your this permittivity is always measured as the constant stress. Only this is the difference, which is true also because you see your permittivity, if you'll study some research papers, you'll get to know that your permittivity, it actually depends on what? It depends on the amount of the deformation of the system. It shows you have deformation dependent permittivity. So your permittivity is going to change with deformation. So you always measure it at a constant speed. Sorry, constant stress. And likewise, your elastic compliance, it is going to change with the electric field, and that is why you measure it as a constant electric field. See, here, if you see, I have written it in terms of ST and everything. But it can happen, like in case of elastic system, we have three-dimensional system. A system can deform in any of the three dimensions. So in that case, we write it in the vector form as Sij. You have, sorry, small s ij kl at a constant electric field. Okay. Then you have t k plus d k ij e at k. Similarly, you can write it as d of I is equals to d I k l t of kl. Here also you're going to have t of kl, and then you are going to have it plus epsilon I k. This is going to be a constitutive relation. And now, depending upon in which direction you are actually applying the electric field and which direction you are giving the deformation, you can give the values to the IJK 1, 2, 3, and likewise. I hope that this is clear. Okay, so coming on to question number 7. For a base excited cantilever beam, del phi by del I is. Firstly, what is a base excited cantilever beam? So if you remember, your base excited cantilever beam was something like this. We had some amount of mass on it. and upon excitation it was having some this kind of. Okay, so let us assume that this angle is your phi, this is your s, and this distance is your v. So if I assume for a very small deformation, okay, for a very small deformation, if I assume, then my sine phi is going to be, tell me what? I have a, if I assume a small deformation, then this s is going to be a straight line. This is going to be my v and this is my phi. So I can write by the law of triangle, sine phi is equals to what? Perpendicular by hypotenuse. My perpendicular is v. So I can write it as v by s, which I can write as v dash. V dash is actually the differential of v with respect to, no, I have to define it as dv by ds because it is small. Okay, because it is small, so it should be a differential element. Okay, I'll just make it over here. dv ds, this is your phi. Cool. Now, if I differentiate this, now, what am I going to get? I'll have v double dash is equal to what? I'll have this as cos phi del phi by del s because I'm differentiating with respect to s. Correct? This is the equation that I get. Now, if you see, for sine phi, I have a relation, and for cos phi, if I want to take out, if you remember that by trigonometry, sine square phi plus cos square phi is equal to what? 1. So from this, I can write my cos phi as what? Under root of 1 minus sine square phi. And my sine square phi is what? V dash, correct? So I'll have cos phi into, sorry, correct? So then I can write my del phi by del s as v double dash into 1 minus v dash square to the power minus 1 by 2. Now, by using the binomial expansion, if you remember, by binomial expansion, we try to expand these kind of terms. I can write it as v double dash into 1 minus, I'll have minus 1 by 2 into v dash square. So I'll have v double dash into 1 plus 1 by 2 v dash, correct? So what is my correct option? This one is going to be my correct option. Okay, I hope that this is clear to you all. Okay, now coming on to question number 8, which says that which of the following is correct regarding torus breakdown route to chaos. Now, when I talk about torus breakdown, firstly, what is a torus? So, if you remember, a torus is something like I have this circle and I have another concentric circle, and then I'll have something like this. This is an example I'm taking for a torus. If you remember that this kind of behavior, if I get for a system response, where was I getting it? I was getting it for a quasi-periodic system. You remember that there was a question also in your assignment. Although this quasi-periodic system is going to show what kind of a shape in the phase plane. It was showing torus behavior, right? So my quasi-periodic response was actually when there was two frequencies, omega 1 and omega 2, which were incommensurate, or we can say that whose ratio was irrational. Okay, so if you remember that when I talked about the route to chaos, I discussed three route to chaos, wherein there was period doubling route to chaos, there was this quasi-periodic route to chaos, and then there was this intermittent route to chaos. So this quasi-periodic route to chaos, if I talk about what was actually happening. In quasi-periodic route to chaos, there was actually, my system was actually having a quasi-periodic behavior. So if my system was having a quasi-periodic behavior, it would have some kind of a Poincare section, should be a closed loop, correct? As I was increasing the parameter, what would happen? If I was increasing my parameter, but this quasi-periodic system was having doubling of the period, period doubling. If you remember, there was this period doubling of the quasi-periodic route. My quasi-periodic response was having some period doubling, right? So that would finally lead to breaking down of the quasi-periodic response into the chaotic response, which means that if my system was having this as my Poincare section, then this would start becoming a strange attractor, something like this. It would lead to some strange attractor, let us say something like this. Something of this form would be my strange attractor. If this is what is happening with the system with the variation of parameter, then we would say that it is actually taking the quasi-periodic route to chaos. So if my system was having quasi-periodic route to chaos, what was actually happening? My Poincare section from closed loop, it got changed into a strange attractor. So what happened actually in the phase plane? Earlier I was having a torus, and because of that torus only I was having a circle or any kind of a closed loop in my Poincare section. So if now that closed loop is getting vanished in my Poincare section, it means that my torus is also getting vanished in my phase plane. My torus has broken down into a what? Strange attractor. Remember that there was this fixed point, this was periodic attractor, there was quasi-periodic attractor, torus you can say, and then there was this chaotic attractor. And when in case of a chaotic attractor, we say that there is the existence of a strange attractor. A strange attractor where the system is always showing the behavior, where the system is always traveling. And that is why our chaotic response is always bounded. It does not let the system to go to infinity. Right. So the question says that which of the following is correct regarding the torus breakdown route to chaos? So the system goes from periodic to chaotic? No, the system is going from quasi-periodic to chaotic, right? So A option is not correct. The system goes from chaotic through period doubling route. This is also not correct. This is a partial correct statement. And I always said that we are never going to consider the partial correct statement as the correct statement, right? So this is also wrong because it is actually telling about the period doubling route to chaos. So the system goes to chaos through the breakdown of torus. Yes, it is going to, because see, if I'll just write it down also. If the system Poincare section changes from a closed loop to a strange attractor with the variation of parameter, then the system has gone through oh no, I've written wrong. Quasi-periodic. Root to chaos. Right. And I hope whatever I wrote is clear. That my system, if my Poincare section is changing from a closed loop to a strange attractor, then my system has gone through quasi-periodic route to chaos. And now, since my system was having some quasi-periodic behavior, it means that it was having torus. And now, since it has changed from closed loop to strange attractor, it means that my torus has now broken down into a chaotic behavior. Correct? So the system goes to chaos through the breakdown of torus. It's a correct option. And the system goes to chaotic through quasi-periodic route. This is also a correct option because both go hand in hand. My quasi-periodic system was having a torus kind of a phase play lot. Okay, I hope that this is clear and you can try solving the equation. I believe that Sir has discussed an example in the lecture. So for that equation, you can use that equation and then try to solve that equation through ODE45 and get how the system is actually behaving. Okay, so the next question is actually MATLAB based question. Okay, but I'll solve it. First, I'll explain to you what a Rosler system is here only. Then I'll solve it in the MATLAB and show you. Okay. So Rosler system. See, I told you that in case of nonlinear dynamics, we take some ideal systems. We take some systems which are used as an example in order to study how my nonlinear dynamics is. So first comes the Rosler system, and my Rosler system is actually a three-dimensional system. Okay, and its equation are given as dx by dt is equal to minus y minus z. Then you have dy by dt as x plus ay, and you have dz by dt as b plus z a minus c. So this is my Rosler system. So if I see, if you see over here, this is a yes. Now, if you see that this Rosler system is a three-dimensional system. Okay, so now if I try to solve this in order to find the solutions, I'll just connect through my laptop now. Just a second. Okay, so is my screen visible to you all? If anyone could confirm.
Yes, madam.
Okay, thank you. Okay, so this is my question. Okay, so I have the parameter values that are given to me, and I have to see whether my system is actually periodic or chaotic. Okay, so I'll just go to MATLAB. I've already written the code, however, you can see this code and you can write it on your own and then try to solve it. Okay, and first we'll see that what are the parameters in the first option. We have A as 0.2, B as 0.2, and C as 5.7. So I'll just put it A as 0.2, B as 0.2, and C as 5.7. Okay, I've taken my initial conditions as 1, 1, 1. I'll just run the code. See, you see, this is my x versus y. This is my x versus time. You can see. Now, I guess you people are very familiar with what is chaos and not. However, I'll still tell you that whether it is chaos or not, we cannot say on the basis of just seeing what the plot is. So what we are going to do, we are going to do what we have been doing. We'll give some initial perturbation into the displacement x, which is very small. So if there is high divergence at after a time, means that my system response is chaotic, otherwise it isn't. Again, run the code. See, see the time response. Can you see it? Up till you can say here, my response both with both the initial conditions was same. But after that, if you'll see the divergence, it has started diverging. And after a amount of time, like near to 1000 unit of time, you'll see that there is a greater divergence of the system response. Okay, so this means that my system response is chaotic. Okay, and there's one more thing that I would like to show you people. See, this is the plot of x versus y. Okay, so you can see that there is this circle kind of a behavior. However, if you'll see this, what is this? What is this kind of a behavior? So for this, we'll try to plot the 3D curve using this. Now you see, you have your x, you have your y, and then you have your z. Can you see what this is? This is a very interesting figure, isn't it? This shows that how your variation is actually happening in the three-dimensional view. Can you see? This shows how my chaotic attractor is, isn't it? And now if you'll try to find the Poincare section, what will it do is, like I have X, Y, and Z, three directions because my system is three-dimensional and I want to see the Poincare section. What will I do? I'll just try to cut a plane in the Z direction. Like for example, I'll take Z is equals to 10 and I'll try to cut it. I'll take up all the points of X and Y that lie on Z is equals to 10 and then I'll see how the system behavior is. So essentially using the Poincare section, I'm actually reducing the dimension of the system. Okay. So coming on to the rest option, the system shows periodic response. No, the system shows chaotic response for this. Yes, your option B is the correct option. So we'll just highlight it. Coming on to third option, I have A 0.35, B 2 and C 4. B 2 and C as 4. Now I'll just run the code. See, can you see? See over here. What is this? Now you have two loops. If you remember, there was this period doubling root to chaos. I have two loops over here, right? And you can see over here also that I have, if I'll just enlarge this, see, there are two maximum peaks, two value of maximum peak and two value of minimum peak, right? So this is what my system response is for this value. So is it periodic or chaotic? It is chaotic. No, it is periodic. You cannot say that this is chaotic. This is periodic. Okay. Remember one thing very clearly, that how would I know? It may happen that after increasing some value, the period doubling can occur, then I'll have four loops. I can have 16 loops. But then how would I know whether it is periodic or chaotic? So I'll just again do what we are good at doing, changing the initial condition and then again simulating. See, again you're having the same phase plot. Your periodic response is the same. I think that I closed the, I'll again plot the time response for your reference. See the time response. Can you see it is actually overlapping? So for a small variation of initial condition, the response is exactly the same. So this means that my response is periodic. It is not chaotic. However, I would like to show you one thing. Let me just change. Let me just try to vary the value of A. Let us just take it as 0.1. See, can you see the system is actually settling at 0? System is actually settling at 0. Correct? Now we'll increase to, let us say 0.2. See, now what is happening? My system is now having a periodic response. Okay. So initially for A 0.1, my system was actually stabilizing at a fixed point. Okay. So it was actually going to a fixed point attractor. Now my system is behaving in a periodic way and it is going to a periodic attractor. Now for 0.35, you people remember there are two loops. So we'll just take maybe 0.36. Again, run the code. Now look over here. System is again having two values of maximum amplitude, two values of minimum amplitude. So it is again having a Periodic response, it is going to a periodic attractor. However, as we have changed the value of parameter from 0.2 to 0.36, the system has undergone period doubling bifurcation. Dynamic bifurcation, by the way. Let us take it as 0.38. Now see what has happened. See over here, over here. If you see very closely, I'm having one, two, three, four. I'm having, I guess, four values of maximum amplitude, and then I should have four values of minimum amplitude. However, it is not very clear in my phase plot because it is also carrying some transient behavior. So I'll just try to plot my phase plot after the transient, taking out the transient. Okay, so I'll just take this line from here. And I'll just plot for some last value. Let us say I have my time as 1000. From 800 to 1000, I'm trying to plot. Now see, now people can clearly see there are four loops. So now when I have changed my parameter from 0.36 to 0.38, though my system is still going into the periodic attractor, but it has again undergone a period doubling bifurcation. Now I'll change it to 3, 9, and again run the code. See, you can think that why is the bifurcation analysis required? So if you remember that I've discussed it earlier also that bifurcation, once it has reached some uh, chaos, it may happen that there could be some intermittent occurrence that after chaos varying the parameter for some point again the system can show some periodic behavior, then again it would go to chaos, and again it can show some periodic behavior, right? So if I know the range of parameter for which my system is stable or for which my system is, I would say, non-chaotic, I can actually tune my physical system in that way. I'm going to tune my this parameter value in the way such that my system should always behave in a periodic manner in order to avoid chaos, because you have seen that my chaotic behavior is so sensitive to initial condition that even a small variation is going to take away the system, right? So chaos is generally avoided. Now you can see over here that my system has gone into chaos. I can see it, but don't believe me. We'll check, we'll write, we'll change the initial condition, and we'll then again plot. Now see. Now if you see over here, can you see? Initially my system behavior was same up to some point, but now it has changed a lot. However, if you'll increase the time of analysis, you're going to see that with time the divergence is increasing very tremendously. Okay, I've taken just 1000 time as 1000 because my system is actually very slow, because I use the recording app also along with MATLAB and this Google Meet. Okay, so I hope that this is clear to you people what I'm trying to tell you, that this is how your bifurcation works. Okay, and if you know that how your system is going to behave, you could set the limit that this is okay, this is how my system is actually behaving, and these are the parameter values for which my system was periodic, and for this parameter value it is non-periodic and everything. So then it would become easier for you, for the design application, that what should be the material, what should be the initial condition given to the system, what should be the parameter values that should be given to the system, so that it would give me the required application, right? It could do the necessary task. Okay, so if I look into the option, the system shows periodic response for this. Yes, this is the correct option. The only difference is that it was having two loops, but it is definitely a periodic attractor. Coming on to question number 10. It is again a question based on your MATLAB, and I have taken this question for Lorentz system, and I have also discussed the Lorentz system earlier also, and I'll not be writing the equation. I hope that you people have now become familiar with the Lorentz system, and if you still have any doubt, you can search it. You can see the books also in order to know that what is the equation for the Lorentz system. So I've already made a MATLAB code for the Lorentz system, as you can see over here, and if you see here, for the Lorentz system, I have the parameters values as sigma as 10, a rho as 14, and beta as 8 by 3. So I'll just put it and check rho as 14 and beta I have as 8 by 3. I have initial condition as 1, 1, 1. I'll just run the code. Now you can see my system actually goes to a steady state. It reaches a particular value. Okay, so it has reached equilibrium. Correct? Fixed point attractor. So system has periodic behavior for this, system has chaotic behavior for this. Both are not correct. It is not having periodic behavior, neither it is having chaotic behavior. It has actually gone to a fixed point response. Okay. Now the second value of parameter is 25. Your row is 25. So I'll just close it. Now you can see over here. Now my response is chaotic. Anyways, we cannot say it like that. We'll change the initial condition and again, okay, we'll just write hold on first. Now I'll again do the simulation. Now you can see it very clearly. My system response is what? It is chaotic because with time my behavior is changing. However, initially up till here it was exactly the same. See, up till here it was exactly the same. Okay, so if I look into the option, the system has periodic behavior for this, the system has chaotic behavior for this. Okay, so the system has chaotic behavior. So this is my correct option. However, since we have considered this, so we'll just try to look into the behavior with the variation of parameter. We'll just maybe take, uh, we'll take 15. We'll run the code. Then we'll take 18. Okay, the hold on was not applied. Okay, so we have to apply a hold on and I'll just remove the color so that we'll be able to differentiate in the phase plot, right? Now see. Now if you see that as I'm increasing the parameter, what is happening to the system? The time that the system is taking to reach the equilibrium point is increasing. Also, the equilibrium point is also changing, right? And there will come a stage, there will come a parameter value at which my system, instead of going to a fixed point attractor, it will start behaving chaotically, or it will start going into the strange attractor. The strange attractor is going to attract the system towards itself. Okay, so this is how you do the analysis for a nonlinear system. So I hope that whatever I taught, it was clear. And this is it for today's live session. And if you have any doubt, you can ask. And next week, we are going to have our last session. So I request you all that if you have any doubt, please feel free to ask either today or in the next week's live session. And I hope that now you people are able to make the code, isn't it? Sachin, if I'll give you a nonlinear
Yes,
equation,
madam.
you'll be able to make the MATLAB code, isn't it?
Yes, madam.
Okay, good. So, do you have any doubt?
No, madam.
Okay, anyone else? Fine then. Next week we are going to meet the last time, and next week we'll conclude this course. Okay then. Thank you. I'll leave
Thank
the
you, madam.
meeting now. Thank you.
Thank